This is one of the, good example to describe, to understand grid design technique. A problem called minimum spanning tree, or simply called MST. Before we proceed, we have to understand what is a spanning tree. Spanning tree of undirected connected graph, which is a graph undirected, which is actually both ways connected, mean we have a node and node connected. Is each connected a cyclic subgraph. What is a cyclic? Cycle means we have the cycle. Cyclic without the cycle. Subgraph without the cycle, which is a tree in general, that contain all the vertices of the graph. If such a graph has weight assigned to its edges, so the connected graph, undirected connected graph with weight, mean we have this, for example, this is the weight. Okay, for this connected graph from the node, the edges have a weight. And now what is a minimum spanning tree? Spanning tree we know already is actually a cyclic subgraph. So minimum spanning tree of the smallest weight, where weight of a tree is defined as the sum of the weight on all its edges. We try to get the total of the weight for all edges. The minimum spanning tree problem is the problem of finding a minimum spanning for a given weighted connected graph. For example, here we have the graph here. This is not a spanning tree. This is a normal graph. And this is a spanning tree where there's no cycle here. A cyclic subgraph. This is a cyclic. There's no cycle here. This also there's no cycle. So there's no cycle. A cyclic with the weight. For this, for example, for this graph, so this is the total weight. These are 6, 9, and 8. For this graph, actually the minimum spanning tree is for the first graph with actually minimum weight, which is 1 plus 2 plus 3 for the graph A, B, C, and D. Okay, now in order to solve the minimum spanning tree, mean to identify whether the graph can be MST, so we have the algorithm, one of the algorithm called Prim's MST algorithm. So start with the T1, the tree 1, consisting of any vertex and grow tree one vertex at a time to produce MST through a series of expanding subtree T1 to T2 until the end, Tn here. On each iteration, construct Ti plus 1 from Ti by adding vertex not in Ti that is closest to those already in Ti. This is called the greedy step, which is actually we want to find that which one the direction. Let's say we have a two direction, A to B, A to C, the junction. We have to find the minimum, because this the greedy. The goal is to get the total of the weight, which is actually the minimum total weight. So in order to find the minimum weight, of course, it's very simple. Just to find every edges with the weight, minimum weight. Okay, stop when all vertices are included. Okay, look at this. I think based on the idea here, we have the graph here, A, B, C until here, H here. This is the weight. This is actually the weight for 4. For the degree, basically, we need to find A and B and D. Which one actually the minimum? Of course, 1 here. And we have to find the rest until from there, at the end, as a result, we can obtain the MST, minimum spanning tree, where the tree, the graph without cycle, or we call it a cyclic graph. Okay, look at this, the idea here. You got the idea. And from this simulation for this graph, okay, here is actually the got 1 and 4, A, B, and D. So we have to find the minimum. Of course, we got the A. Finally, here others C, F, E, G, I, J, H, and finally this is actually the spanning tree. But the minimum spanning tree based on the graph here, and the algorithm can obtain the minimum spanning tree, where we have this all actually the minimum, and we total this actually the minimum compared to others combination. Okay, some notes about Prim's algorithm prove by induction that this concession actually yield MST. There is a proof there. Actually, based on the by induction, the Prims obtain the MST, minimum spanning tree. Net parity Q for locating clauses brings vertex, which is actually the parity Q is the principle of Q first in first out, but first in first out here based on that the parity value, which is for here is the minimum value of the h, the weight. And for the efficiency is O n squared for weight metric representation based on the metric representation of the graph and array implementation of the parity Q end up with n squared. But for the list agency link list here, obtain m log n. M log n here, which is actually the um, minimum heap n vertices and m edges, which is m edges and vertices, and minimum heap impedance of priority q.